Assalamu alaikum and good morning, everybody. I'm Dr. Aisha Khalik from National University of Sciences and Technology, and I'm the co-organizer of this conference. I welcome you all to this first session of the last day of the conference, and this is a very special session. We have Professor Vahid Karimipour with us. Vahid is my long-term collaborator, and he has hosted me many times in Iran, to the beautiful city of Tehran and Kish Island. He is indeed a very well-known and the most prestigious quantum physicist working in Iran. He actually started his career as an electrical engineer, and then he moved to physics and did his PhD in physics, and now he's a professor in Sharif University since 2001. And he has worked mostly on the theoretical aspects of quantum information, focusing on inversion of quantum channels, multipartite entangled states, and quantum communications in the absence of reference frames. And he has been associated with many journals. He's editor of European Physics Journal D and International Journal of Quantum Information. And he's also an outstanding referee of American Physical Society. He is a Simon Associate of International Center for Theoretical Physics in Trieste, Italy. It's very kind of him that he has accepted our invite. In fact, Iran also runs a series of Iran International Conferences, Conference on Quantum Information and Computation, two of which I have attended, and it's a very well-established series. We hope to reach that point from this, while starting it this year, that we could host so many speakers as they do in person in Iran. So we are really following you that how to reach that point. So please welcome Professor Vahid Karimipour for a wonderful talk now. Thank you very much.
Thank you, Aisha. Thank you very much. Let me share my screen. Do you see my screen now? Do you see the presentation?
Yes, we can see that.
Okay. And thank you, Aisha. Thank you, Mohsen and Peter, for inviting me to this wonderful conference. And I hope that through these conferences and more collaboration, the scientific communities of Iran and Pakistan will come closer together and can contribute to the international science. I'm very happy to be in this activity, and I enjoyed a lot the previous days and the beautiful talks. And I hope that I can contribute also to some extent. This is a beautiful picture from Islamabad, I think, that I took from internet. I hope that someday I can go there in person. The work that I want to talk about is quasi-inversion of quantum and classical channels. And this is the work that I started 2 years ago with Fabio Benatti and Roberto Florianini in Trieste. We did it for qubit channels, and then I extended this for higher dimensional channels with my students and with Karol Zizkowski in 2021. So the details are in these two papers. And of course, I will not talk about the details. I will talk about only the main ideas. And I hope that this presentation can be useful for those who are interested in this concept, and then can go to the papers for proofs and for details. So let's start with the basic idea. We all know that a unitary map can be inverted. So if you have a state like psi, and you act on it by a unitary operator u, you can then act by u minus 1 on psi prime to take back your state. And then you can do this for any state. So if all the states psi 1, psi 2, psi 3 go to psi 1 prime, psi 2 prime, psi 2, 3 prime, etc., then you can convert back the final states to the original states. For example, if you have made a mistake or something like that. The question that we ask is it possible that a quantum map or a quantum channel be inverted? Because we know that in quantum information theory, we are concerned with quantum maps, quantum channels, or completely positive trace-preserving maps. And we ask if there is a channel like E, which maps rho to rho prime, is it possible to turn back rho prime to rho? Not for one single row, for all rows. We want to completely inverse the quantum channel, not for single row, but for all rows. Technically, this means that if the channel E has a cross decomposition like the one given here, sigma m, km rho, km dagger, is it possible to design another quantum channel like E minus 1 with a different cross decomposition, different cross operators, so that it inverts the action of the original channel? Is it possible to do so or not? And of course, everybody knows that, we all know that the answer to this question is no, we cannot. For a very simple reason, because we all know that if you act by a channel E on states, the distance between states decreases after the channel. The states become more similar to each other, as is shown in this picture. You have a state rho 1, which is depicted by the yellow color. Then we have a state rho 2, which is depicted by the red color. And then you act on these two states with the channel E. Then the final state is somehow similar to both rho 1 and rho 2. So they have become similar to each other, and the distance between them has decreased. So if you act on the final states by another channel, the distance increases further, and you cannot put them back to the original position. This theorem can be proved rigorously, but we can get an idea of, by an example. For example, suppose that you consider this example, the partial trace. We all know that the partial trace is a legitimate quantum channel. And if you have two figures like the ones that we have here, one is sad emoji and the other is a happy emoji, and then you take the trace on the lower part, you'll find two emojis which are almost similar to each other. So in this way, you have decreased the distance. And this is the property that every quantum channel has. Every quantum channel decreases the distance between the input states and increases their fidelity. So while the answer is no, we can ask for another question. The other question is that, is it possible to, I don't know why it's, okay. Is it possible to do an approximate inversion? Suppose that we have a channel E. No, we do not want to exactly take back the original state. We want to approximately get back the original state. So we want to invent a quasi-inverse channel, which we denote by this EQI. QI stands for quasi-inverse. It has its own cross decomposition, and we want to design it such that the final states after this E and then EQI is close to the original states. We show that it cannot be exactly the original state. We want it to be almost the original state, not for one single row, for all rows. If we think of it about in terms of the Bloch-sphere, the situation is something like this. We have a Bloch-sphere here with various states on this, on different positions, which I have denoted by different colors. And then the channel E distorts this quantum Bloch-sphere to an ellipsoid. And the ellipsoid has been distorted. It has been stretched in various directions. And it has been rotated and translated. And the colors have been mixed and so on and so forth. And as you see, there is a little similarity between this original shape of the Bloch-sphere and the final shape. But the question is, can we act on this distorted Bloch-sphere by some quantum channel EQI so that it is still in some sense similar to the original channel? So as you see by the colors, by the position of the colors, you see that The final ellipsoid is somewhat more similar to the original ellipsoid than this middle one. So we want to ask for the presence of such a quasi-inverse and its properties, if it exists. More technically, we want to do this. We have a quantum channel E, and we want to find the average fidelity for all the states. Call it f bar of E. So when you take the initial states, and then you find the final states, and you take the average between input and output, average over all input states. We want to act on E by a quasi-inverse, which we call EQI, and we want that the average fidelity increases between the input and output. This is the requirement 1, and the requirement 2 is that we want to do this in an optimal way. So f bar of EQI OE should be higher than f bar of E prime OE for all E prime channels that you find. So I try to answer this in 2 parts. First for the qubit channels, and then for the higher dimensional channels. And as we will see, the qubit channels is much simpler than the higher dimensional channels. Let's do this for qubit channels. And I try to review some of the basic properties of quantum qubit channels that we know. You all know all of these things, but one of the joys of life is to listen to things that you already know. So what a qubit channel does? A qubit channel does this. This is the original density matrix. A qubit channel maps this to another qubit states whose Bloch vector instead of R is R prime. So I should, okay, is R prime. And R prime is an affine map of R. So R prime is equal to M times R plus T. M is a matrix. It shouldn't be positive. It shouldn't be Hermitian. It's only real, and T is a vector. And this is all that a qubit channel does to the density matrix of qubit states. It's an affine transformation on the Bloch vector. And in shape, it does this. You have a Bloch sphere, and then after the map, the Bloch sphere is shrunk in different directions, it's rotated, and it's also translated with respect to the origin. This translation is due to this T, which is here. If the channel is unital, it means that T is equal to 0. So this is the elementary concepts of qubit channels. And what we mean by the average fidelity of a channel, we take the original input state to be a pure state, then we act on this pure state, and this is the output states, and then we take the average fidelity between, we take the fidelity of this output state with the input state, and then we take an average over all the input states. And this quantity can be calculated easily, and it has nice properties. If you note that the original state is a pure state, so it's on the surface of the Bloch sphere. It has a unit vector n. Then the output vector is r. It's inside the Bloch sphere. And then if you calculate the fidelity of these 2 states, and then take the average, you will find that the average fidelity is this simple quantity. It doesn't depend on T. It only depends on M in this very simple way. Trace of M is the quantity which determines the average fidelity. So once we are given this, then the question is this. If we have a channel which has this affine transformation, can we append another quantum channel, which we call quasi-inverse? It has the, so to say, affine transformation MQI and TQI. And if you combine these two, you will find that the affine transformation of the combined channel is MQIM times MQIT plus TQI. But fortunately, the average fidelity depends only on this first part. It doesn't have anything to do with the translation part. So the average fidelity of the combined channel is this simple quantity. And then the problem reduces to maximizing this trace, maximize trace of MQI M. If we find the matrix MQI so that this quantity is maximized, then it means that we have solved the problem. But the problem is not finished here, because not every channel, not every matrix that you find is the affine transformation of a legitimate quantum map. Every quantum map corresponds to an affine transformation M, but the converse is not true. You cannot take a matrix M and call this the affine transformation of a quantum map. It has some severe restrictions. So let's proceed in this way. The first thing that we note is that the average fidelity is a linear function. Is a linear function on the space of the channels. This is the definition of the average fidelity, and you will easily see that this function is a linear function in terms of E. It means that if the quasi-inverse that you find has a decomposition in terms of simpler channels, like lambda E1 plus lambda E2, then you can take, if lambda 1, for example, is greater than lambda 2, you can take E1 to be the quasi-inverse. It does the better job, because you know that we want to find the quasi-inverse in the optimal way. It means that if this EQI in the space of channels has a decomposition in terms of two simpler channels, then you can take one of these channels to be the quasi-inverse. This means that the quasi-inverse can be an extreme point. The extreme points of any map, of any convex map, are the points that cannot be decomposed further. So this point is not an extreme point. None of the points on this red line is an extreme point, unless except the two extreme points E1 and E2. They cannot be decomposed further. So what we have found here that due to linearity of the average fidelity, the quasi-inverse can be an extreme map, extreme point. And the other point, the other property is that the quasi-inverse of a qubit channel can be chosen to be unital. And this is a very important property because it happens only to be true for qubit channels. And the reason is quite simple. For the moment, we try to show the quantum channels with their affine transformations. And we see that if MQI and TQI is a channel, you can simply erase TQI and put it equal to 0, and you obtain still a channel. In this way, you can unitarize a channel. And the reason is quite simple. If you have a channel which distorts the Bloch sphere here, it rotates it, it shrinks it, and then it translates it, then you can neutralize the translation, and then you are still inside the Bloch sphere. So in this way, you can unitarize every quantum channel. You erase the translation part, and you obtain another specific and legitimate quantum channel. This is only true for qubits, in a way that we will see why this is not true for higher dimensional channels. So a qubit channel, which is both extreme and unital, is a unitary map. And this is a well-known fact. In fact, all the qubit channels have been classified and have been characterized by Meribet, Ruskai, and her colleagues. And the space of all unital qubit channels is unitarily equivalent to Pauli channels. And the Pauli channels, you see that correspond to these tetrahedra. The vertices of this tetrahedron correspond to conjugation by the Pauli matrices. This is the identity channel. This is Pauli, the Pauli channel sigma X. This is sigma Y. This is sigma Z. These are unitary channels. And these are the four extreme points of the space of channels, of the space of unital qubit channels. These points on this line, they are unital channels, right? But they are not extreme. because they can be decomposed in terms of I and sigma x. The points on this line are not extreme because they can be decomposed in terms of sigma y and sigma z. The point on this face, they are not extreme because they can be decomposed in terms of I, sigma y, and sigma z. So the only points which are unitary and are unitary on these four vertices, which are unitary maps. So in this way, we can find the quasi-inverse of all qubit channels. Every qubit channel has such a decomposition. It is a unitary, then a standard canonical map EC, and another unitary nu. And the characteristic of this EC is that its affine transformation is diagonal, which we call lambda, lambda 1, lambda 2, lambda 3. And you can order these diagonals in some way. And then depending on the position of these lambdas, you can find the quasi-inverse. And I will not go into the detail. The only final result is that depending on whether lambda 2 plus lambda 3 is greater than 0 or less than 0, you find two different quasi-inverses, which are actually two different unitaries depending on these lambdas. You find two specific unitaries which rotate back the Bloch sphere in a way which is more similar to the original form of the Bloch sphere. Now we come to the higher dimensional channels. And even before you go to the concept of quasi-inverse, we all know that the higher dimensional channels and qubit channels have not been classified. Their structure is much more difficult and much more complex than the qubit channels. We do not have the Bloch sphere anymore. And many things that we take for granted for qubit channels are not true for higher dimensional channels. Let's see how. The first thing is that we do not have the simple Bloch sphere. In qubit case, all the states lie in a sphere, and a unit sphere, and the pure states are the boundary of this sphere. For the d-dimensional states, the only thing that we know is that the space is convex, and it's high dimensional. Because, for example, if you go to Q-traits, this space becomes 8-dimensional. If you go to, for example, 4-dimensional states, this state becomes 15-dimensional. And nobody knows what is the exact shape of these things, because the exact shape requires that you diagonalize these 8 or 15-dimensional matrices and determine their positivity, which we know that analytically is impossible. So we do not have the exact and analytic knowledge about the shape of these d-dimensional states. This is the first thing. We only know that still you have such a representation. You can write again rho equal to 1 over di plus r dot gamma. These gammas are matrices which are d squared minus 1 dimensional, and they have 0 trace, and they are Hermitian. Only this one. We know that, and you can also normalize them in a way that will be useful later. So the second property that we have, in fact, the second nice property that we do not have, what we like to have, is that this set is not symmetric anymore. For the qubits, we had a symmetry. If R is a Bloch sphere, minus R is also a Bloch sphere. If R is the Bloch vector of a legitimate density matrix, minus R is also the Bloch vector of a density matrix. For the higher dimensional case, this is not the case anymore. Let's see by this example. This is the general form of the density matrix. Now suppose that you have only one of these gammas, right? In principle, we should have d squared minus 1 gammas. But let's suppose that R is only 1-dimensional. One of the components is non-zero, all the other components are 0. And let's call that gamma to be equal to H. This is a traceless matrix. This is Hermitian, and this has the required normalization that was pointed out in the previous slides. Now, suppose that we take a rho in this form, 1 over 3 I plus h. If you do this calculation, I plus h becomes 0, 0, and this number will be 3 divided by 3. You have 1, and this is a pure state, right? And now suppose that I convert this plus to minus. And then we will have 1/3 1 minus h. 1/3 minus h, I minus h is 2, 2 minus 1, which is not a state at all because it has a negative eigenvalue. So this means that the space of higher dimensional states, of higher dimensional, so to say qubits, is not symmetric at all. The third property that we had in qubit case, but we do not have here, is that unitalization is not possible. So you cannot erase simply that T and obtain another channel. If you have a channel with affine transformation M and T, you cannot erase simply T and you obtain another channel. This is not possible. And again, the reason can be seen very easily. Suppose that this is the space of the channels, right? The space of the, the space of qubits, for example. Then what a channel does is that it rotates, then it shrinks it, and as you see, part of this space is outside the space of states, and this translation T removes this anomaly and puts the final space of states again inside the original legitimate space of states. So this is what the channel does. It shrinks, rotates, and then it puts back the states by this translation into the space of density matrices. And if you remove that translation, it's no guarantee that the final states is a density matrix, is a positive matrix. So this means that unitalization in high dimensional states is not possible. You cannot convert a channel with affine transformation in T to M0. So we have lost many of the good properties that we had for qubits, and yet we still want to find the quasi-inverse. Let's see if we still can do this or not. The only thing that we retain from the qubit case is that the quasi-inverse is again an extreme channel. And this is due to the linearity of the average fidelity. If we had used, for example, the averaging over mixed state, we have lost that linearity and we could not retain even this simple property. So we have to review a little bit about the quantum channels in D dimensions. The first thing that we want is the Choi-Yamilkovsky matrix. If this is a channel E, the Choi matrix of this channel can be written in this form, right? And K alpha is this Choi vectors, so to say. Psi plus, phi plus is the maximally entangled state. These K alphas, of course, need not be orthogonal to each other. So this is not the spectral decomposition of C, but it can always be put into this form. This is the Choi matrix of any channel. For any channel, we can find a Choi matrix, and many of the properties of the channel are encoded in the Choi matrix. For example, the Choi matrix should have unit trace, the Choi matrix should be positive, and so on and so forth. The other thing that we want about the channels is the dynamical matrix. Another way of looking at the channels is in this way, as big superoperators. Suppose that we have a row, I take it for the qubit case, we have a row which is a 2x2 matrix. We can always put this into the vector form. This is called vectorization. So instead of a matrix A, B, C, D, you are dealing with a vector row, which is called A, B, C, D, a row vector. Then the same channel that we had before can be recast in this form, like elementary matrix operation. You have a vector row, you have a new vector E of row, and there's a matrix phi of E, d squared by d squared, which does this map. And the expression of phi of E can be written in this form in terms of the Krauss operators, sigma alpha, K alpha, tensor product K alpha star. And there is a simple relation between phi chi, between the dynamical matrix and the Choi matrix. It's called reshuffling, but we do not need it now. Then we come to the average fidelity. We want to proceed step by step and define the average fidelity, its linearity, and then imitate the steps that we took for the qubit case. The average fidelity is defined in the same way as before. We take the input states to be pure. Then we act on the input states and obtain the output state, which is E of psi psi. And then we take the fidelity of this state, and then we take the average over all states. And then if you calculate this, after a long calculation, this is not as easy as the qubit case, we will find this one. This is the dimension of the states, and this is the trace of the dynamical matrix. So what we want is that we want the matrix, we want the channel phi EQI, so that its dynamical matrix phi of EQI has the property which maximizes this one. So this is the goal. The goal is to find an E prime which maximizes trace of phi E prime phi E. And again, we have that limitation. Not every dynamical matrix that you write corresponds to a channel, or not every matrix is a dynamical matrix of a quantum channel. This is the basic difficulty and the basic obstacle that we have. But we have a basic theorem. The basic theorem that we prove is that no matter what E prime is, there's always an upper limit to this trace of phi E prime phi E. This is the basic theorem that we will use. This quantity, this trace, is always less than D, which is the dimension of the states that you are considering, times lambda max. What is lambda max? Lambda max is the highest value of the eigenvalue, highest eigenvalue of the Choi matrix of the channel E. So this is our basic theorem. We do not know if this is saturated or not, but we look for those channels in which or for which this inequality is saturated. So here we have an open problem. We do not have solved this problem in its full generality. This is still an open problem. But we have examples for this, for channels, such that when you find phi E of prime, this inequality is saturated. And so we have a rather large class of channels for which we can find the quasi-inverse in closed form. But again, I stress, we do not, and we have not found the quasi-inverse of all qubit channels. This is still an open problem. Let's see a few examples. So, as I said, I introduced some examples, some class of examples for which this equality holds, right? If this equality holds, due to this inequality in the box, we know that phi EQI is really a quasi-inverse of phi E. And EQI is really a quasi-inverse of E. So we look for those channels for which such equality is true. Let's see. Example 1, mixture of orthogonal unitaries. And note that we are talking about orthogonal unitaries, not any unitaries. So I still stress that for a channel which is a mixture of unitaries, we do not have the quasi-inverse yet. But for a channel which is a mixture of orthogonal unitaries, so that B alpha and B beta are orthogonal to each other, then we have the quasi-inverse. It's a simple matter to find the Choi matrix of this. The Choi matrix of this channel is already in the diagonal form, and it's enough to find the largest eigenvalue. Sorry. And we find that the quasi-inverse is the unitary map for which lambda max, for which the PM is the largest. So if you have a mixture of unitary maps which are orthogonal, to find the quasi-inverse, it's only necessary to find the maximum P which P is maximum, you find that P, call it PM. It corresponds to a VM, and then the quasi-inverse VM dagger rho VM. This is the best that you can to invert the channel. You find the maximum P, and then you find the corresponding unitary, which is called VM, and VM dagger rho VM is the channel that we want. This is the first example, a mixture of orthogonal unitaries. Example 2. No, we are not dealing with unitaries, but conjugations. So X alphas need not be unitaries. But the point is that the mixture is uniform. So here we do not have any factor, P alpha, we do not have any P alpha here. So we have a uniform mixture of orthogonal conjugations. And we find that EQI is exactly the same, except that X alpha is replaced by X alpha dagger. So in a sense, these channels are their own inverse. In a sense, if you forget about this conjugation. And you can calculate the quasi-inverse, the average fidelity before the quasi-inverse and after the quasi-inverse. Before the quasi-inverse, it's 1 over D plus 1, which you see as D goes higher and higher, the average fidelity becomes lower and lower in terms of 1 over D plus 1. But after the quasi-inverse, we have this quantity. Note that if Q is equal to 1, right, it means that we have only one conjugation. So the map is unitary. Then after the quasi-inverse, the average fidelity is 1. It should be, because we know that any unitary can be exactly inverted. But and also when Q goes to infinity, if you have a large number of orthogonal conjugations, F bar of EQIE is the same as the F bar of E. So we do not succeed in increasing the average fidelity. But between these two extremes, we can really achieve some increase of average fidelity. Channels which are their own inverses. This is the famous Landau-Streeter channel, which is written this way. And then you can find that its quasi-inverse is the same. This channel can be its own quasi-inverse, and you can also convert, generalize this to any other group. You take any group like G, then you have the generators of that group, and then you take a specific representation. This CMU is the Casimir generator of that group, and these are channels, generalized Streeter, Landau-Streeter channels, and they have their own, they are their own inverses. And finally, the example 3, which is transpose depolarizing channel. We know that the transpose channel is not a channel, right? In fact, this is the property that Asher-Press used to invent the criteria of separability, because the transpose is a positive map, but it's not a completely positive map. But the point is that if you mix this with the identity map delicately in this form, so that P is between D over D minus 1 and D over D plus 1, you still have a legitimate quantum channel. And this was done by Holevo and Werner, I think. P should be between these two extremes, D over D minus 1 and D over D plus 1. Then you have a channel which is called transverse depolarizing channel. And these channels have two parameters, P and D. Here we have the P here, and here we have D. And you know that for the 2 dimensions, for qubits, P lies between 2 over 3 and 2. And as you go up, as the dimension goes up, these interval becomes narrower and narrower. And then for D infinity, you really find E0 of rho completes the mixed channel. And this part, this extreme channels, this E minus, are called Werner-Holevo channels. And what we found is that for every channel here, for every channel that you have here on this line, the quasi-inverse is this Werner-Holevo channel. Again, by analytic arguments, which you will find the details of which in these two papers. In the second paper, you will find the arguments and the proofs for this. So the result is that for any channel in any line, the quasi-inverse is this extreme E minus channel, Werner-Holloway channel. And the increase of average fidelity is given by this formula. So let's see how much time we have. Okay. The title, as you noted, was the quasi-inverse of classical and quantum channels. So I spent a few slides to talk about the quasi-inverse of classical channels. We have the quantum channels, and we are used to talk about quantum channels, but the quantum channels are the classical analogs of, they have their own classical analogs. The classical analogs are stochastic matrices. So instead of density matrices, you are dealing with probability vectors, probability distributions. A classical channel is nothing but a map which takes a probability vector and maps it to another probability vector. This T is called a stochastic matrix. And all the properties that we had for quantum channels have their own counterpart here. For example, instead of trace preserving property, instead of positivity, we have that all these elements of this matrix should be positive because they are probabilities or probability transitions. And instead of the trace preserving property, we have the fact that every column should add to 1. This blue box means that all these elements should add up to 1. This is the analog of trace preserving property. And the analog of unitality means that all these rows should add up to 1. This is an extra condition. If a matrix has this extra condition, then it's called bi-stochastic. In quantum case, it means that the channel is unitary. It's not a necessary condition for all channels, but for specific types of channels, if this is the case, that channel is, or that stochastic matrix is called bi-stochastic matrix or doubly stochastic matrix. So the question is, what is the inverse of a stochastic matrix? Suppose that we have here T, which is a stochastic matrix. As you see, all these elements are positive. The sum of every column is 1. When you take the actual T minus of this matrix, you find the actual T minus is this matrix, which is not stochastic at all. The elements are not positive. They do not sum to 1. So the question is, for a general two-dimensional stochastic matrix, which we write in this form, what is the quasi-inverse? By quasi-inverse, again, we mean a matrix which is stochastic and which has the which is playing the role of a quasi-inverse or an approximate inverse. And for that, we have to define an average fidelity. The average fidelity between the fidelity between two probability distributions is defined in this form. And then if you take the, if you take the average over all input states, you'll find a simple relation that it's equal to 1 over the trace of D, trace of T, which is the stochastic matrix itself. So the quasi-inverse is quite simple. Maximize this trace of T prime T, provided that T prime is a stochastic matrix itself. So in the space of stochastic matrices, search for those matrices T prime which maximize this quantity. This is the recipe that we have. And then I will give you only the recipe. For example 1, which is the full space of stochastic matrices of 2 dimensions, we have only 2 parameters, x and y are limited to these square. And the quasi-inverse is this. For all these channels here, for all the stochastic matrices here, we cannot do any inversion. The best that we can do is to leave it intact. So the quasi-inverse is 1. But for these parameters, sigma x, the Pauli matrix, which is itself a stochastic matrix or a permutation, can do the job. Example 2, when we go to higher dimensions. Suppose that we have this matrix, this stochastic matrix, still you can check that this is a stochastic matrix because all the elements are positive and they sum to 1. And the recipe is this. I leave the proof to the papers. The recipe is this. In each row, take the higher elements, the largest element. Here I have highlighted these largest elements. And the first row is 3/4, and here, 5/8. Then replace them by 1 and erase all the other things, right? So I have put 1 here and here and here. And then transpose the matrix. In this special case, the transpose is the same as the previous one. This is the quasi-inverse that we have. You cannot do better than this. And this is, of course, a permutation. As you see, this is both stochastic and biostochastic, and it's still a permutation because a permutation matrix just permutes all the elements. There's a permutation. Example 3, take this matrix, right? And here you have these larger elements, 1/4, 7/8, 2/3 in each row. And then convert it to 1, put all the other elements equal to 0, and transpose it. Here we have a matrix, a TQI, it's a stochastic matrix, right? Because the elements are positive, the sum of all rows is 1, but it's not a permutation because the permutation has the property that in each row and each column you should only have 1, 1, but this is not a permutation. So there are stochastic matrices whose quasi-inverses are not permutation. And then we have further examples, but I think that with this, I have come to the end of my talk. So to summarize, we have found the complete solution of quasi-inverse for qubits. We have found large examples or classes of quasi-inverse for qubit cases. The general solution is still an open question, and we have found the complete solution for the classical stochastic matrices. Thank you very much for your questions, for your attention, sorry. Thank you.
Thank you very much, Vahid, for a very interesting talk. This is the best thing I like about your talks. You start from the very basic and take us through the whole journey to the ultimate. And we have some couple of questions here. So it's what is the advantage of symmetry apart from mathematical simplicity on the previous slide, on the slide that you showed earlier?
So this is in the chat box or?
Yeah, they are in the chat box. You can read them if you like.
Let me see.
So everybody, please put your questions in the chat box. Till Vahid is still here.
I see the chat box, not the question and answer. Let's see. Okay, let's. Okay, say the question, please. Again, what is the advantage of symmetry?
The advantage of symmetry apart from mathematical simplicity?
No, actually, it's a mathematical simplicity. When you go into the proof, you will see that really it plays an important role. If you do not have that symmetry, you cannot solve the problem.
Mm. Okay.
Okay.
Is there a physical advantage to it as well?
And okay. Kindly elaborate the relation between PM and PI. Yes, PI's. The PI was the contribution of each unitary, right? PM was the largest one. So you pick up only the largest PM, and then you find the unitary corresponding to that PM, and then you invert it.
Okay. Right. So if anybody else has any other question, please post your question in the chat, replying to everyone.
Oh, I see Nigam, my friend here. So.
Yeah. So if there's no other question, we thank Vahid, and we hope, Vahid, that in our next session, we can have you in person here in Pakistan, since you have visited two times to Pakistan. So I hope that you would be interested in coming again.
Yeah, sure.
Thank you very much.
Thank you very much.